Usually, when you think about the physical space around you, right, like your home or maybe your office, you feel a certain sense of security because you can visibly see the boundaries.
Right, the physical walls.
Exactly. You see the walls, you see the locks on the doors. Maybe there's, security camera up in the corner. If someone actually tries to break in, there is a tangible physical barrier right there.
Yeah, you can physically see the threat.
But right now, as you are listening to this deep dive, there is this invisible, totally silent battle happening on the router sitting in your living room or, on the massive rack of servers at your workplace. Every single second of every single day, there are automated scripts, botnets, these sophisticated actors basically rattling the digital doorknobs of your network.
And it is entirely invisible, which is the scary part. And it is relentless. I mean, most of us rely so heavily on these networks for literally everything, our livelihoods, our entertainment, our personal data.
Yeah.
Yet we often just, plug in a generic plastic box provided by our internet service provider.
Yeah, the one they just hand you when you sign up.
Exactly. We see the little green lights blinking on the front, and we just falsely assume, okay, we are safe.
We treat it exactly like a household appliance, don't we? Like you plug in a toaster, you get toast. You plug in a router, you get Wi-Fi, and you literally never think about it again.
Until it stops working.
Yeah, exactly. But as cyber threats evolve at this, frankly, terrifying pace, those traditional, rigid, plug-and-play consumer routers, they just aren't cutting it anymore. Relying on them is kind of like locking your front door, but leaving every single window on the ground floor wide open.
That's a really good way to put it.
So our mission today is to completely change how you view that blinking box. We are doing a comprehensive deep dive into a platform called pfSense. We're going to unpack the actual mechanics of how this software can take standard everyday hardware and transform it into this enterprise-level fortress.
And I mean, it really is a massive paradigm shift from hardware-defined to software-defined security. The architecture we were pulling apart today, it represents a fundamental change in how network security is deployed. By the end of this conversation, you will understand the exact mechanisms required to build a smarter, faster, and just significantly more secure network. And the absolute beauty of this architecture is that it applies whether you are, managing a massive enterprise data center or just putting together a personal home lab to protect your own devices.
It scales all the way up and all the way down. But before we get into the heavy technical weeds, I do need to quickly mention that this deep dive is brought to you by Penn Content Digital. Okay, so let's start at the absolute foundation. What exactly is pfSense and why is it causing such a massive disruption in the industry right now?
Well, at its core, pfSense is an open source firewall and routing platform, and it's based on an operating system called FreeBSD.
Now, I know FreeBSD is an operating system, but why build a security platform on that instead of, say, Linux or Windows? Everyone knows those.
That's a great question. So FreeBSD has this legendary reputation in the networking world, specifically for its network stack.
Okay, it's network stack.
Right. The way it handles routing packets of data at really high speeds is incredibly stable and very mature. It was built from the ground up to be a robust server operating system. It's not a desktop OS that just had a graphical interface bolted onto it later.
Oh, I see. So it's purpose-built for this kind of heavy lifting.
Exactly.
Yeah.
When you are building a firewall that might need to process gigabits of traffic every single second without crashing or dropping packets, you need an underlying operating system that is fundamentally bulletproof. And that is exactly what FreeBSD provides. It's a rock-solid foundation for the pfSense software to run on top of.
Yeah, no, that makes total sense. But the thing that really stands out to me when looking at the broader landscape of network security is the stark contrast between pfSense and those traditional big-name hardware firewalls.
Oh, it's night and day.
Yeah.
Traditionally, if an enterprise wanted top-tier network security, they were basically forced to purchase these wildly expensive proprietary hardware appliances from massive vendors.
The big metal boxes.
The big metal boxes, yeah.
Yeah.
And these are entirely closed systems. So you buy their physical box, you pay these exorbitant ongoing licensing fees just to keep the features active.
Wait, you have to pay just to keep the features you already bought turned on?
Oh yeah, yearly subscriptions, just for the privilege of using the firewall features. And on top of that, you are entirely dependent on that specific vendor's timeline for software updates or security patches or even just new features. pfSense flips that model completely upside down because it is open source and fundamentally modular.
It feels to me like buying a traditional hardware firewall is like buying a fully built prefabricated house. It's totally rigid. If you suddenly decide you want a third floor or a different layout, you can't just change it. You literally have to buy a whole new house.
Exactly.
But pfSense is more like getting the ultimate architectural blueprint along with an endless supply of raw materials completely for free. You dictate the hardware and the software molds to it.
That's exactly how it works.
But I gotta push back on this open source concept a little bit.
Yeah.
If the underlying code is just out there on the internet for anyone to see, including malicious hackers, how can enterprise environments or hospitals or IT professionals actually trust it to defend against sophisticated cyber criminals? I mean, doesn't the word free kind of imply a lack of professional-grade security?
Yeah, and that is definitely the most common hesitation people have. But actually, in the cryptography and cybersecurity world, open source is generally considered far more secure than closed source.
Really? How so?
There is this concept called Linus's Law, named after the creator of Linux, which basically states, given enough eyeballs, all bugs are shallow. Because the pfSense code is entirely open, it isn't just relying on a small, isolated team of developers at one corporate office somewhere to find vulnerabilities.
Right, because there's a whole world of people looking at it.
Exactly. It has this massive global community of independent cybersecurity experts, penetration testers, network engineers, all constantly auditing the code. They are probing it for flaws and contributing patches in real time.
So instead of security by obscurity, meaning like, we hope the hackers don't figure out how our closed the box works, it's security by radical transparency.
Precisely. Relying on obscurity is a really fragile defense. If a closed-source vendor misses a bug and a hacker finds it, that vulnerability might exist in the wild for months before the vendor even realizes it, let alone issues a patch for it.
That's terrifying.
It happens all the time. But with an open-source model, the community is often aware of and actively patching vulnerabilities the moment they are discovered. And if we look at the macro trends driving the industry right now, this kind of rapid adaptability, it's basically non-negotiable at this point.
Right, because the whole environment has completely shifted. It's not just a few static desktop computers sitting in an office building anymore.
Not at all. The landscape is totally unrecognizable compared to just a decade ago. I mean, we have seen this massive migration to cloud infrastructure. Organizations are moving their critical databases and applications entirely off-premises to AWS or Azure or Google Cloud.
Which means the firewall has to do way more than just guard the front door of the office.
Exactly. That means they need secure, seamless, and really high-speed connectivity between their physical office buildings and these virtual cloud environments. The firewall isn't just protecting a physical building. It has to secure the invisible pathways going up to the cloud.
And then you add the whole remote work explosion on top of that.
Oh, the shift to remote work fundamentally shattered the traditional network perimeter. In the past, the firewall was literally a moat around the corporate castle.
Yeah.
If you were inside the office plugged into the wall, you were trusted.
Right.
But now, you've got employees logging in from coffee shops, their personal home Wi-Fi, airport lounges, hotel rooms. The perimeter is basically evaporated. You also have massive regulatory pressures now, compliance frameworks like HIPAA for healthcare, PCI DSS for payment processing. You can't just check a box on an audit form anymore. You have to mathematically prove your network architecture prevents unauthorized access.
Which leads right into this concept of zero trust networking. I've heard this buzzword thrown around a lot, but looking at the actual mechanics of it in the sources, it's fascinating. So the zero trust model essentially dictates that absolutely no user, no device, and no application should be trusted by default.
None of them.
Right. Even if I am using a company-issued laptop sitting inside the company office, plugged directly into the corporate switch, the network should still look at me and say, prove who you are, prove your device is secure, and prove you have explicit permission to access this specific file.
Yes. Zero trust is basically the death of that castle and moat analogy we talked about. In zero trust architecture, every single room inside the castle has a biometric lock, and every single hallway has an armed guard. You don't just get the keys to the entire kingdom just because you somehow made it past the front door. You have to continuously authenticate and authorize every single digital interaction. And to actually enforce those incredibly strict micro-perimeters, you need a routing platform that can manage thousands of granular, highly specific rules simultaneously without just totally choking.
So how does pfSense actually execute this? Like, if zero trust means trusting no one by default, how exactly does the platform act as the ultimate bouncer at the door? This brings us into its advanced firewall rule management, because the mechanics here, they go way beyond a simple allow or deny switch.
Way beyond it.
We have granular rule creation, interface-based policies, aliases, stateful packet inspection, and schedule-based rules. Let's break down the actual logic here. Granular rule creation means the administrator isn't just saying allow all web traffic. They are writing policies like allow user A on this specific device MSC address to access database B, but only on port 443 and literally drop everything else.
The precision is the point. And that precision is applied via what we call interface-based policies. A robust pfSense deployment rarely just has two ports, one for the internet and one for the local network.
Right. Usually there's a bunch.
Yeah, you might have a physical interface for the fiber internet connection, another interface just for the internal accounting network, a totally separate interface for the guest Wi-Fi, and an interface dedicated entirely to internet-connected security cameras.
Oh, I see.
And pfSense evaluates its rules sequentially from the top down, completely independently for every single interface. So a packet of data arriving on the guest Wi-Fi interface is judged by a completely different set of laws than a packet arriving on the accounting interface.
But practically speaking, managing all of that sounds like an absolute logistical nightmare. If an enterprise has, say, 500 employees, 3,000 devices, and a dozen different servers, writing and maintaining individual IP address rules for every single interaction would be a full-time job for a whole IT team. How do you manage that kind of complexity without constantly breaking the network?
Yeah, it would be impossible. And that is where the concept of aliases and object management becomes crucial in pfSense. Think about how a firewall actually reads a rule. It doesn't read human names. It reads IP addresses and port numbers. But humans are terrible at remembering massive lists of random numbers.
Right. I picture aliases like a VIP list at an exclusive club. Instead of the bouncer, which is the firewall, having to memorize the individual faces, names, and ID numbers of 500 different people who are allowed into the VIP room, the club manager just hands the bouncer a single clipboard labeled VIP list.
Exactly.
The bouncer just checks the clipboard. If you want to add or remove someone from the VIP section, you don't rewrite the bouncer's entire rulebook in his head. You just update the names on that one clipboard.
That is exactly how it works on the back end. An alias in defense is just a variable. You create an alias called, let's say, accounting PCs.
Yeah.
And you populate it with the 50 IP addresses belonging to the accounting department. Then you write a single firewall rule. Allow alias accounting PCs to access the financial server.
Okay, that makes sense.
Right. So if you hire a new accountant, you don't touch the firewall rules at all. You just add their new IP address to the alias, and the rule dynamically applies to them. It dramatically reduces the complexity of the rule set, which in turn drastically reduces the chance of human error. And frankly, human error is responsible for the vast majority of security breaches.
Oh, for sure. Let's dig into the actual inspection process, though, because there is a massive distinction here that really defines modern firewalls, the focus on stateful packet inspection. What exactly makes a firewall stateful, and mechanically, how does that differ from the basic, plastic routers most people have at home?
So to understand stateful packet inspection, or SPI, you have to understand how devices actually talk to each other on the internet, specifically using the TCP protocol. TCP requires a three-way handshake to establish a connection.
A handshake.
Yeah. Device A says, hello, I want to talk, which is called a SYN packet. Device B replies, hello, I acknowledge you want to talk, which is the SYN ACK packet. Then device A says, great, I acknowledge your acknowledgement, which is the final ACK packet. Only then does the actual data start flowing between them.
It's a very polite, structured conversation.
Very structured. Now, older primitive firewalls use stateless inspection. They looked at every single packet of data in total isolation. They would look at a packet and check a static list. Is this coming from an allowed IP? Yes. Is it going to an allowed port? Yes. Let it through. It had absolutely no memory of the conversation.
Kind of like a security guard who checks your badge, lets you into the building, and then when you walk past them again 5 minutes later to go to the bathroom, they have no idea who you are and demand to see your badge again, verifying every single detail from scratch.
Yes. And from a security standpoint, that's incredibly dangerous. An attacker could craft a malicious packet that looks like a legitimate reply to an ongoing conversation, and a stateless firewall would let it right through because the isolated details matched the rule.
Wow.
A stateful firewall, however, monitors the actual state of the connection in a dynamic memory table. It watches that three-way handshake happen in real time. When your computer reaches out to a web server to ask for a web page, pfSense records that specific outgoing request in its state table. It notes the internal IP, the external IP, the source port, the destination port, and the exact sequence numbers of the packets.
So it's actively tracking the context of the entire conversation.
Exactly. When the external web server sends the web page data back, the firewall intercepts it, looks at its state table, and says, I'm expecting this exact traffic because my internal device explicitly asked for it. It dynamically allows the reply traffic through without needing a specific permanent rule allowing inbound traffic from that web server.
Well, that's smart.
But if a random packet suddenly hits the outside of your firewall without any internal device having initiated a conversation first, the firewall checks its state table, finds no record of a request, and instantly drops the packet into the void.
That is brilliant. It's not just reading the words, it's verifying the grammar and the flow of the dialogue. And you can also add a dimension of time to this logic, right? Using schedule-based rules. Why is manipulating time an important security feature?
Because operational reality dictates that access needs change based on the clock. Think about a school district, for example. The firewall might have rules allowing access to certain educational video platforms or internal testing servers. But do students or staff really need access to those internal testing servers at 2:00 a.m. on a Sunday?
Definitely not. I mean, if data is moving from the testing server at 2:00 a.m., someone is either stealing the test or holding the server for ransom.
Precisely. With schedule-based rules, you apply a strict time parameter to the firewall policy. You configure pfSense so that the rule allowing access to those critical servers is only active from, say, 7:00 a.m. to 5:00 p.m. Monday through Friday. Outside of those precise hours, the rule essentially evaporates.
It just disappears.
The door doesn't just lock. It ceases to exist for the network's perspective. It's a highly effective way to shrink your attack surface when the IT staff isn't actively awake and monitoring the network.
Okay, so the perimeter is incredibly tight. We have the stateful bouncer checking the context of every single conversation, consulting dynamic VIP lists, and strictly enforcing curfews. But a locked front door, no matter how smart the lock is, isn't enough. What if someone breaks a window? What if a legitimate employee accidentally carries malware into the building on a USB drive? You need active security patrols roaming the interior, looking for suspicious behavior. And this introduces us to intrusion detection and prevention systems, the IDS and IPS.
This is the critical layer where pfSense elevates from a highly intelligent traffic cop into an active threat hunter. A firewall decides who can talk. An IDSE decides if what they are saying is dangerous.
And there are two distinct systems commonly integrated into pfSense for this, right? Suricata and Snort. Before we get into how they analyze traffic, let's look at the mechanical differences between them. The documentation describes Suricata as a high-performance, fully integrated engine, while Snort is a widely used compatible tool. What does it actually mean under the hood?
The primary difference historically comes down to how they utilize the physical hardware, specifically the processor. Snort was originally designed as a single-threaded application. That means no matter how many cores your CPU has, Snort can only use one of them to process a specific stream of network traffic.
Oh, I see.
If you have a massive 10 gigabit fiber connection,
Sure.
a single CPU core is going to max out and bottleneck the entire network trying to inspect all those packets sequentially.
It's like having a 4-lane highway funneling into a single toll booth. Everyone has to wait.
Exactly. Suricata, on the other hand, was built from the ground up to be multi-threaded. It can take that massive fire hose of network traffic, split it up, and assign different streams to different CPU cores simultaneously. It can process significantly more data at much higher speeds. Both use very similar logic to detect threats, but Suricata is generally favored in modern, high-bandwidth enterprise environments purely because of its multi-threading capabilities.
So we have this multi-threaded engine analyzing the traffic, but how does it actually know what a threat looks like? We have intrusion detection, the IDS, and intrusion prevention, the IPS. I understand the IDS is basically the alarm system. It watches the traffic that the firewall allowed in, analyzes the payload of the packets, and if it sees something bad, it logs it and alerts the admin, but it doesn't stop it.
Correct.
The IPS is the active guard that actually severs the connection and drops the malicious packets. But my main question is, if these are such advanced systems, why do they constantly require signature updates? I mean, shouldn't an advanced threat hunter just inherently know what malware looks like?
That touches on a really fundamental challenge in cybersecurity. How do you define a threat? The IDS and IPS engines process traffic against the massive database of signatures. A signature is a specific sequence of bytes or a string of malicious code or a known behavioral pattern that identifies a specific cyber attack.
So they are the digital fingerprints of known crimes.
Yes, exactly. When a hacker writes a new piece of ransomware, Cybersecurity researchers capture it, reverse engineer it, identify its unique fingerprint, and write a new signature rule for it. Suricata takes that massive database of tens of thousands of signatures and compares every single packet traversing your network against it.
Okay, checking the fingerprints.
If a packet matches the signature for, say, the WannaCry ransomware, the IPS instantly drops the packet. But the system is entirely dependent on knowing the fingerprint beforehand.
So if a hacker alters their code even slightly, creating a new variant,
The fingerprint changes. And if your database hasn't been updated with that new signature, the IPS will look right at the new ransomware, compare to its outdated lists, see no match, and let it walk right into your network.
oh, wow.
That is why daily, sometimes even hourly, signature updates are the absolute lifeblood of the system. Without them, you have a false sense of security. You are guarding against the attacks of 2022, not the attacks being invented this morning.
Okay, so we have the perimeter locked, and we have Suricata constantly scanning the interior traffic against a constantly updating database of known threats. But let's bring this back to the reality of the remote worker. We established earlier that the perimeter has basically dissolved. Legitimate employees need to teleport from their home Wi-Fi directly into this highly secure corporate environment. We can't just open a port and hope for the best. We have to construct secure, encrypted tunnels straight through the public internet.
Right. And this requires robust virtual private network, or VPN capabilities. If you are going to embrace a distributed workforce, the strength of your VPN architecture is arguably the most critical component of your external security posture.
We have a whole suite of options within pfSense, right? WireGuard, OpenVPN, and IPsec. Let's look at the mechanics of these protocols, starting with WireGuard. It's often described as a modern marvel. I look at WireGuard like a sleek, high-speed bullet train. It's known for extreme simplicity, a tiny code base, and just incredible performance. But if WireGuard is so superior, why does pfSense bother supporting and constantly updating older, heavier protocols like IPsec and OpenVPN?
It's important to understand why WireGuard is so fast. Older VPN protocols are incredibly complex. They have hundreds of thousands of lines of code because they try to support every single cryptographic algorithm invented in the last 30 years.
Just to be compatible with everything.
Yeah. WireGuard took a completely different approach. It supports only a handful of the absolute fastest, most modern cryptographic primitives. Because it doesn't have to spend time negotiating which encryption method to use with the other side, it connects almost instantly. And its code base is less than 4,000 lines long.
Which means it's much easier to audit for security flaws, right? Finding a bug in 4,000 lines of code is much easier than finding one in 400,000 lines.
Exactly. It's a much smaller attack surface. For a remote workforce, say, an employee connecting their laptop from a hotel room back to the corporate server, WireGuard provides an incredibly fast, lightweight remote access VPN that barely impacts the device's battery life or the internet speed. But, as you asked, why keep IPsec?
Right.
Because enterprise networks are heavily burdened by legacy hardware.
The heavy freight trains.
Right. Imagine a Fortune 500 company. Their central data center might be running multi-million-dollar routing hardware that was installed 5 years ago and relies entirely on IPsec for site-to-site connectivity. IPsec is an industry standard. It operates at the kernel level and offers incredibly deep, complex authentication methods like IKE2. If you are deploying a new pfSense firewall at a branch office in London and it needs to create a permanent, invisible, secure tunnel back to the legacy hardware at the headquarters in New York, you must use IPsec. pfSense supports it because it needs to be the ultimate interoperable Swiss Army knife.
And OpenVPN, where does that sit in the hierarchy?
OpenVPN is the incredibly versatile middle ground. It uses SSL/TLS for key exchange, which is very similar to how your web browser secures HTTPS traffic. Its greatest strength is this ability to disguise itself.
Disguise itself.
Yeah. If an employee is working from a country with strict internet censorship or from a corporate client's office that actively blocks VPN traffic, OpenVPN can be configured to route its traffic over TCP port 443.
Which makes the VPN tunnel look exactly like normal, secure web browsing traffic to the outside world.
Yes, the external firewall just sees encrypted web traffic and lets it right through. It's incredibly reliable, and there are client applications available for literally every operating system out there. An administrator needs the flexibility to choose WireGuard for pure speed, IPsec for legacy site-to-site tunnels, and OpenVPN for maximum compatibility and firewall evasion.
Okay, so a remote employee securely tunnels into the network. They are inside the fortress. But looking again through the lens of zero trust, once they step out of that VPN tunnel, we cannot just let them roam the entire building freely. If a sophisticated attacker manages to compromise that employee's home laptop and rides the VPN tunnel directly into the corporate network, we need a way to contain the blast radius. We have to partition the internal network itself.
Which brings us to the architectural strategy of network segmentation. And this is primarily achieved through VLANs, or virtual local area networks.
The best way I can visualize a VLAN is to look at the design of a military submarine. A submarine is divided into multiple watertight compartments. If the hull is breached and water starts violently flooding into the forward torpedo room, the crew can immediately seal the massive steel doors, isolating that specific compartment. That room might flood completely, but the watertight doors prevent the water from spreading to the control room or the engine room. The submarine as a whole survives.
That is literally the perfect analogy for network segmentation. In a digital environment, the flooding water is a cyber threat, a ransomware worm spreading, or a hacker who just gained a foothold. The watertight steel doors are your VLANs, enforced by the strict CESA's firewall rules between them.
Let's apply this to a real-world scenario that terrifies a lot of network administrators. IoT, or the Internet of Things, smart TVs, internet-connected thermostats, smart speakers, Wi-Fi refrigerators. Think about your own home network right now. Why does it actually matter if your cheap smart TV is sitting on the exact same network as your work laptop or your personal server?
It matters immensely because IoT devices are an absolute cybersecurity nightmare. They are built for convenience and low cost, not security. They are frequently manufactured overseas with hard-coded administrator passwords that the user literally cannot change.
Oh, that's wild.
They use outdated, minimal Linux kernels, and the manufacturers almost never release firmware security updates for them once they are sold. To a cybercriminal, a smart light bulb or a Wi-Fi thermostat is the easiest possible entry point into your life.
So if my smart TV gets compromised,
If your smart TV is on a flat network, meaning everything in your house is in one giant pool and it gets compromised, the attacker now has an active command post inside your perimeter. The pfSense firewall at the front door is no longer protecting you from them because they are already inside the house. From that TV, they will scan the local network, locate your work laptop, find a vulnerability in your file sharing protocols, and extract your data. This is what we call lateral movement.
they enter through the weakest link and pivot laterally. So how does pfSense physically stop this using VLANs? What is the actual mechanism?
It uses an industry standard called 802.1q VLAN tagging. You take your physical network switch and you logically divide it. You tell pfSense to create a dedicated VLAN just for IoT devices. Let's call it VLAN 20. You put the smart TV, the thermostat, and the smart speakers into VLAN 20. Then you put your trusted work laptop and your personal servers into VLAN 10. When a packet of data leaves the smart TV, the network switch tags that packet with a digital label that basically says, I belong to VLAN 20.
And when it hits the pfSense firewall,
The firewall looks at the tag, looks at its rules, and enforces the watertight door. You write a rule that says, devices in VLAN 20 are allowed to access the external internet to stream video or check the weather. However, they are absolutely forbidden from initiating any communication with VLAN 10.
so the door only opens one way. If my laptop in VLAN 10 wants to cast a video to the TV, it can reach into the IoT network. But the TV can never initiate a connection back into the secure network.
Precisely. If the smart TV gets completely overtaken by a botnet, the hacker is trapped inside the flooding compartment of VLAN 20. They can't move laterally because the pfSense firewall explicitly drops any packet tagged with VLAN 20 that tries to cross the boundary.
That's amazing.
And you apply this exact same logic to a corporate environment. The HR department's computers processing sensitive payroll data must be on a separate VLAN from the marketing department. And guest Wi-Fi is the most extreme example. You give visitors an internet connection, but their VLAN is completely isolated from the corporate servers. You eliminate the risk of lateral movement entirely.
Okay, this architecture is incredibly secure. We have stateful rules, IPS engines, encrypted tunnels, and watertight VLAN compartments. But here is the friction point every network admin faces. If the network is so heavily scrutinized and locked down that the internet connection becomes sluggish or worse, goes offline completely, the business grinds to a halt. And if the business stops making money, the security architecture is viewed as a total failure.
Absolutely.
How does pfSense balance maximum security with the reality of keeping the traffic flowing smoothly?
Security cannot come at the expense of operational availability. I mean, a perfectly secure network that drops VoIP calls every 5 minutes is a useless network. This requires us to look at pfSense's capabilities regarding high availability, multi-WAN, and traffic shaping.
Let's tackle traffic shaping and quality of service, or QoS, first. I want to use a different analogy here instead of the standard highway traffic idea. Let's think about a hospital emergency room triage system. If someone walks into the ER with a sprained ankle, they need attention, but they can wait in the lobby. If someone is wheeled in with a severe trauma, they bypass the lobby entirely and go straight into the operating room. They have absolute priority. How does pfSense act as that triage nurse for digital traffic? If I'm on a critical video conference call and someone in the next office starts downloading a massive 100-gigabyte database, how does pfSense mechanically ensure my video doesn't freeze into a robotic mess?
It uses sophisticated queuing algorithms. Without QoS, a basic router treats all packets equally. It's a first-in, first-out system. If the 1 gigabyte download fills up the router's buffer, your small video conference packets get stuck at the back of the line. By the time they finally get transmitted, they arrive too late. In real-time communications like VoIP or video, packets arriving late is called jitter, and it destroys the call quality.
So how does the QoS algorithm fix the buffer?
An administrator configures traffic shaping rules based on port numbers, IP addresses, or even the type of protocol. You tell pfSense traffic utilizing the SIP protocol for voice calls or traffic coming from the executive boardroom IP addresses is priority level 1. Large file transfers over FTP or HTTP are priority level 5.
Right, triage.
When the network gets congested, pfSense creates multiple queues. It actively delays or drops the packets from the file download, literally slowing down the download speed to guarantee that the VoIP packets never wait in line. It reserves guaranteed bandwidth for the critical operations, acting as the ultimate triage nurse.
That handles the congestion perfectly. But what happens if the physical connection to the outside world is severed? What if a backhoe down the street cuts the fiber optic cable? The sources emphasize multi-WAN, load balancing, and automatic failover.
For any modern organization, relying on a single internet service provider is a massive single point of failure. Multi-WAN allows pfSense to manage multiple wide area network connections simultaneously. You might have a primary high-speed fiber connection and a secondary slower 5G cellular or satellite connection plugged into the same box.
How does the system handle the transition if the fiber gets cut? Does the admin have to log in and frantically flip a switch?
No, it relies on automatic failover, driven by gateway monitoring. pfSense is constantly sending ICMP ping requests, just these tiny diagnostic packets, out to a reliable external server, like Google's DNS servers, over both connections. It monitors the latency and packet loss continuously. The absolute millisecond the fiber connection stops returning those pings, pfSense marks that primary gateway as down.
And the routing tables update dynamically.
Instantly. It rewrites the internal routing rules to funnel all outbound traffic through the secondary 5G connection. State tables are flushed and rebuilt over the new connection. For the end user, they might experience a momentary stutter on their video call, but their connection stays alive.
Yeah.
And beyond just WAN failover, pfSense supports hardware high availability using a protocol called CARP.
Wait, hardware failover, meaning two separate physical pfSense boxes.
Yes, the common address redundancy protocol. You have a primary physical firewall and an identical backup physical firewall. They share a single virtual IP address. They're constantly syncing their state tables and configurations over a dedicated cable. If the primary firewall literally catches fire or someone trips over the power cord, the secondary box instantly assumes the virtual IP address and takes over the routing. The network doesn't even realize the primary box is dead. It is the ultimate insurance policy for business continuity.
That is insanely robust. So pfSense manages the triage of the traffic and ensures the physical paths are resilient. But to efficiently route all this traffic, the system needs to constantly consult the Internet's phone book, the domain name system, or DNS. And diving into how pfSense handles DNS reveals some fascinating intersections between routing, security, and privacy.
Oh, absolutely. DNS is often the most overlooked vulnerability in a network. Every single time you type a human-readable web address into your browser, your computer has to ask a DNS server to translate that name into a machine-readable IP address.
And historically, the mechanics of that request were a massive privacy nightmare. If I understand correctly, standard DNS queries are sent across the internet in plain text over port 53. It is the equivalent of writing a list of every single store, clinic, and political organization you plan to visit today on a postcard and handing it to the mail carrier. Anyone who handles that postcard, your internet service provider, the coffee shop Wi-Fi admin, or an attacker on the network can read exactly where you were going.
Exactly. Even if the website itself is fully secured with HTTPS encryption, meaning the attacker can't see the passwords or data you enter on the site, the initial request to find the site is completely exposed. They see the metadata of your life. ISPs actively mine this plaintext DNS data to build advertising profiles on users.
So how does pfSense secure the phone book? It integrates a feature called DNS over TLS, or DOT, right?
Yes, DNS over TLS takes that plaintext postcard and seals it inside a cryptographic tamper-proof envelope before it ever leaves your network. pfSense can be configured to act as the central DNS resolver for your entire network. When your laptop asks for a website, it asks pfSense locally. pfSense then takes that query, encrypts it using TLS encryption over port 853, and sends it to a secure upstream DNS provider. The ISP sees you are sending encrypted data, but they have absolutely no idea what website you are asking for. It basically blinds the eavesdroppers.
And because pfSense is managing the DNS internally, it can also act as an aggressive filter before the request even leaves the building. This leads right into the extensible package ecosystem. One of the most powerful add-on packages available for pfSense is pfBlockerNG. It essentially weaponizes the DNS resolver to perform malware domain protection. How does that mechanism work?
It uses something called the DNS sinkhole, or a DNS black hole list. Cybersecurity organizations maintain these massive, constantly updated lists of domains that are known to host malware or command and control servers for botnets, or aggressive tracking scripts. pfBlockerNG downloads these lists directly into the pfSense DNS resolver.
So if an employee accidentally clicks a highly sophisticated phishing link in an email,
The employee's computer tries to look up the IP address for that malicious phishing domain. It asks pfSense. pfSense checks its pfBlockerNG list, sees the domain is flagged as malicious, and instead of returning the real IP address, it returns a null address, just a blank page. The connection is severed at the root level before the employee's browser can even attempt to connect to the malicious server.
it's incredible. And pfBlockerNG doesn't just do DNS filtering, it does IP filtering, specifically geo-IP blocking. This seems like a fascinating way to reduce the attack surface.
It's one of the most effective, low-effort security measures you can possibly implement. The internet is global, but most businesses are local. If you run a regional logistics company in the American Midwest, your employees, your vendors, and your clients are all in North America. There is no legitimate operational reason for an IP address originating from a server farm in Russia or North Korea or a known cybercrime haven to be initiating a connection to your mail server or your VPN portal.
Right, if they are knocking on the door, they are up to no good.
So with pfBlockerNG, you download the GeoIP databases, which map the globe's IP addresses to specific countries. You select entire continents or specific high-risk nations, and you write a firewall rule that simply says, drop all incoming traffic originating from these regions. You instantly render your network invisible to millions of automated scanning bots probing from overseas. You drastically reduce the noise in your firewall logs and massively shrink your threat landscape.
Let's touch on a few other critical packages that expand pfSense's capabilities. We have Squid Proxy and ACME. How do they fit into the architecture?
So Squid is a web proxy cache. If you have a school with 500 students and they all need to download the exact same 1 GB Windows update on Tuesday morning, that would completely cripple the internet connection.
Yeah.
Squid Proxy intercepts the very first download, saves a copy of the update locally in the pfSense hard drive, and when the other 499 computers ask for it, pfSense serves it instantly from the local cache, saving massive amounts of external bandwidth.
That's super efficient. And ACME.
ACME automates the management of SSL and TLS certificates, specifically integrating with services like Let's Encrypt. If the security certificate on your VPN portal or your web server expires, web browsers will throw massive security warnings and VPN clients will outright refuse to connect. The business goes down. ACME automatically reaches out, verifies your domain ownership, and renews those cryptographic certificates before they expire, completely removing the risk of a human just, forgetting to update a calendar reminder.
And finally, NUT, Network UPS Tools. This allows pfSense to talk to your uninterruptible power supply. If the building loses power, the UPS battery kicks in. NUT monitors the battery level, and when it reaches, say, 10%, it initiates a graceful shutdown of the pfSense operating system, ensuring the file system doesn't corrupt when the battery finally dies.
Yeah, it's all about systemic resilience.
Okay, we have built a phenomenal architecture here. We have stateful packet inspection, multi-threaded IDSIP engines, encrypted zero-trust VPN tunnels, strict VLAN segmentation, multi-WAN failover, and encrypted DNS sinkholing. We have built an absolute digital fortress. But a fortress is only as strong as its weakest guard. And that brings us to the reality check. Best practices, the challenges of managing this beast, and how it scales in the real world.
Because the most advanced technology in the world is totally useless if the human configuring it makes a foundational mistake.
And there is a paradox of choice here, isn't there? pfSense gives you access to every single dial, switch, and routing table. The configuration complexity is immense. With this level of granular control, isn't there a massive risk of human error? Couldn't I be trying to set up a new VLAN, write a rule in the wrong order, and accidentally sever my own secure remote administration connection, permanently locking myself out of my own firewall?
Yes. That happens to network engineers way more often than they like to publicly admit. When you are writing firewall rules, pfSense evaluates them sequentially. If you accidentally place a deny all rule above your allow management interface rule, the firewall reads the deny all, applies it, and drops your connection immediately. You are locked out. That is the double-edged sword of an enterprise-grade tool. It gives you enough rope to build a suspension bridge or enough rope to hang yourself.
So how do organizations mitigate that risk mechanically?
It requires adhering strictly to the principle of least privilege and rigorous configuration management. Not every IT help desk staffer needs root admin access to the firewall. You enforce multi-factor authentication, or MFA, on the admin portal, requiring a hardware token or an authenticator app so a stolen password isn't a total compromise. But the most important safety net is the XML backup system.
Having a save point, basically.
Exactly. pfSense stores its entire complex configuration, every rule, every alias, every VPN setting in a single, easily readable XML file. Before an administrator applies a massive change to the routing tables, they download that XML file. If they make a catastrophic mistake and break the network, they don't have to spend hours troubleshooting. They plug a laptop directly into the physical console port, upload the XML backup, and the firewall reverts to its exact state from 5 minutes ago. It takes seconds to restore.
The other challenge that constantly comes up is performance tuning and hardware compatibility. Turning on every single feature we just discussed, running Suricata across all interfaces, loading massive PF blocker and G lists, handling hundreds of encrypted WireGuard connections. That has to require significant processing power, right?
Oh, it requires massive computational resources. If you don't scale the physical hardware correctly, the firewall itself becomes the bottleneck and the network grinds to a halt. For instance, VPN encryption relies heavily on mathematical calculations. Modern processors have specific instruction sets, like AES-NI, baked directly into the silicon to handle cryptographic math efficiently. If you install pfSense on a cheap, outdated CPU without AES-NI, the processor will hit 100% utilization just trying to encrypt a single 1 gigabit VPN tunnel. You absolutely have to match the hardware architecture to the software demands.
Which explains why the exact same pfSense software can be found in wildly different deployment scenarios. We see a huge community of home lab enthusiasts running it.
Yes, network engineering students or tech enthusiasts will install pfSense on an old, repurposed desktop PC or a low-power mini computer. They use it to experiment with VLANs, learn how to configure IPS engines, and protect their home networks from IoT vulnerabilities. It's an incredible educational tool because it's completely free.
But then you take that exact same software image and you scale it up to a massive retail chain. A retailer might use it to build hundreds of site-to-site IPsec VPNs, securely connecting every retail store's point-of-sale system back to the central data center to process credit cards, ensuring compliance with those PCI DSS regulations.
Or consider a healthcare environment. A regional hospital network relies on pfSense running on redundant, high-availability enterprise servers with massive multi-core processors. They use strict VLAN segmentation to ensure the life-saving medical devices are physically isolated from the guest Wi-Fi. They use the IDSIP to monitor for ransomware that might target electronic health records, ensuring strict compliance with IPA privacy laws.
The software interface is identical. The core FreeBSD architecture is the same. The only difference between the home lab and the hospital is the scale of the hardware and the architectural wisdom applied to the configuration.
Precisely. It is infinitely scalable.
So we know where the architecture stands today. We know how it's deployed from living rooms to data centers. But the cyber threat landscape is a perpetual arms race. The adversaries never sleep. Where does this platform go from here? What are the technological trends driving the future of PF?
The industry is rapidly pushing pfSense to evolve further into what we call a next-generation firewall, or NGFW. The perimeter is going to continue to dissolve, which means we will see even deeper zero-trust integration natively within the routing policies. We are also looking at major advancements in SD-WAN.
Software-defined wide area networking. How does that differ from the multi-WAN failover we discussed earlier?
Multi-WAN is somewhat reactive. A line goes down, traffic moves to the backup. SD-WAN is highly proactive and application-aware. Imagine a company with 50 branch offices connected by multiple different internet links, some expensive fiber, some cheap broadband. SD-WAN allows the firewall to actively monitor the health, latency, and jitter of every single path in real time. It can dynamically say, send the sensitive VoIP traffic over the high-quality fiber link, but route the bulk file backups over the cheaper broadband link. It optimizes the entire global network dynamically without human intervention.
That is incredibly efficient. Another trend that stands out is the move toward containerized deployments. The traditional visual of a firewall is a heavy metal box with cables sticking out of it, sitting in a server rack. Does containerization mean the physical box is disappearing entirely?
In many cloud-centric environments, yes, it does. Containerization technologies like Docker or Kubernetes allow complex applications and all their dependencies to be packaged into a standardized, lightweight digital unit. Supporting containerized deployments means pfSense isn't tied to bare metal hardware. You could spin up a fully functional virtual pfSense firewall instance within an AWS cloud environment or on a tiny edge server in a remote factory in a matter of seconds using automated deployment scripts.
The firewall becomes liquid. It isn't a physical appliance anymore. It's just code that flows to exactly where the infrastructure needs to fence instantly.
It allows for infrastructure as code. When a development team spins up a new virtual network for a project, a containerized firewall is automatically spun up alongside it, pre-configured with the exact security policies required. But the most critical advancement on the horizon is undoubtedly the integration of AI-assisted threat detection.
And this seems absolutely necessary given how the adversaries are evolving. We talked at length about Suricata and the IDC IPS engines relying on signature databases, the digital fingerprints of known threats. But what happens when the attackers stop using static tools? We are seeing the rise of polymorphic malware powered by artificial intelligence. Malware that automatically rewrites its own source code and alters its digital fingerprint every few seconds.
A static database of signatures becomes virtually useless against polymorphic attacks. The threat hunter won't recognize the disguise because the disguise is entirely novel every time. To counter AI-driven cyber attacks, the defense must deploy machine learning. AI-assisted threat detection moves the firewall beyond static human-written rules. The AI engine sits on the network and spends weeks analyzing the flow of traffic, establishing a highly complex mathematical baseline of what normal behavior looks like for your specific organization.
It learns the rhythm of the business.
Exactly. It knows that the accounting servers usually talk to the database servers at 10:00 a.m., transmitting roughly 50 megabytes of data. If suddenly, at 3:00 p.m., a desktop computer in the marketing department starts opening thousands of encrypted connections to an unknown server in a foreign country, the AI engine flags it instantly. It doesn't need a signature. It identifies the threat because the behavior is mathematically fundamentally abnormal. It can identify a zero-day attack, a vulnerability never before seen by anyone in the world, and drop the connection autonomously. It elevates the real-time observability and response capabilities to meet the demands of modern AI-generated attacks.
It basically becomes an AI versus AI arms race at the network edge. Okay, we have covered an immense, staggering amount of architectural ground today. Let's summarize the mechanics of this journey. We started with that simple, vulnerable, blinking box in a living room, and we have unpacked the exact mechanisms pfSense uses to transform that concept entirely. It is not just a router, it is a modular open-source command center built on a bulletproof FreeBSD foundation. We explored how granular stateful packet inspection rules police the perimeter. We looked at how multi-threaded IDSIPS engines actively hunt for threats using signature databases. We discussed utilizing advanced cryptography like WireGuard for secure remote access tunnels, and how to construct watertight VLAN compartments to prevent lateral movement of compromised IoT devices.
And we balance that security with operational resilience, detailing QoS traffic triage and multi-WAN high availability to ensure the business never goes offline, while leveraging encrypted DNS and GeoIP blocking to massively shrink the digital footprint.
It is a phenomenal suite of capabilities that addresses every single layer of modern network vulnerability. But as we wrap up, I want to leave you with a final lingering thought based on everything we've dissected today. We have talked extensively about how open source platforms like pfSense are democratizing enterprise-grade security. They are making zero-trust architecture, high-availability failover, and next-gen firewall capabilities completely free and accessible to anyone, from a multi-million-dollar hospital data center down to a curious enthusiast building a home lab.
which is an incredibly positive advancement for our global cybersecurity posture.
It is. But think about the flip side of that democratization. What happens when these exact same incredibly powerful, adaptable, and free networking tools are equally available to the very adversaries we are trying to keep out? The attackers can just download pfSense, set up identical lab environments, and run millions of automated tests against the firewall logic to find the microscopic cracks in the armor. As the tools to defend the network become universally accessible, the technology itself is no longer the advantage. The true differentiator won't be the software you own. It will be the architectural wisdom, the discipline, and the strategy you apply when configuring it.
The battlefield has been completely leveled. The invisible battle happening on your router just evolved from a game of who has the biggest budget into a highly complex, strategic game of chess.
Exactly. The software provides the pieces, but you have to know how to play the board. And that is why understanding the mechanics behind these concepts is more critical now than ever before. Thank you for joining us on this incredibly deep dive into network architecture. The next time you walk past that blinking box providing your Wi-Fi, I hope you view the invisible data flowing through it through a completely new structural lens. Stay curious, stay secure, and we will catch you on the next deep dive.